the quantum mechanical model of the atom. Now with chapter 2, what's really important for us is just to bring about what the heck were people thinking. Now, what's amazing about this chapter and why it's one of my favorites is that it gives us, again, the history, the background. Where did we come from? Some of the big name players in the development of quantum mechanics. Now, this is really taking the atomic model straight to where we are today. The atomic model explains the strange behavior of electrons. It wasn't until the early 20th century that scientists began to investigate the quantum realm, the subatomic realm. Now, 20th century, this is around 1910 to 1920. 100 years ago, we still did not know what the heck was going on with the subatomic realm. And it was not until this time, until scientists started to investigate and seeing different results depending on what lab you were in. And that's where these main scientists, Albert Einstein, Niels Bohr, de Broglie, Max Planck, Heisenberg, Dirac, and Schrödinger, and some others, but these were the main players, started to really investigate together this quantum realm, this really, really small, what about these electrons? And why are people getting weird results depending on their experiment setup? Who's wrong? Who's right? And so their investigation really laid the foundation of our current understanding of matter. A lot of these scientists really hated quantum mechanics at the end of the day. It is very complex. It is very, very pull your hair out. I don't understand it, but it works. For everything that we can think about, these scientists really brought us into this new realm of understanding how electrons behave. Not that long ago either. And so all of these scientists pretty much did is develop the idea that electrons are small, but the atom depends on the electrons. So even though we look a lot at mass and we do a lot of mass conversions in the lab and we're looking at the protons and the neutrons solely for that, we don't want to forget about the electrons. And they were pretty much overlooked up until the early 1900s. Just a little bit of background in this. If you've ever heard of the Schrödinger cat theory, let's just explain what that was. Schrödinger developed this theoretical paper. He wrote it. It was a paper published early 1900s. However, it was a theoretical paper. He did not actually do this, but he was trying to explain exactly what quantum mechanics was trying to explain, but for the everyday scientist. Now, not the everyday person, the everyday scientist. So still somebody that was understanding of chemical behavior, but that's how complex this actually is. He took a cat, theoretically. This is why my family told me, don't go be an artist, go be a chemist. Here's my cat. Nice. And he put him in a box, theoretically, right? Now, also in there, he put a vial of hydrocyanide, which is poison. Sad day. He sealed it though. He was a good chemist. He sealed it with a radioactive isotope that was set to decay and release the poison to the cat. Super awesome. He sealed this box all up and he said, this is an electron. Now, if you think that this is crazy, yeah, he might have been a little nuts because of quantum mechanics. But think about it. He said that before observation, so before he opens the box, right? Opening the box to see if the cat is is still there, alive or dead. He said, before I open this box, I've sealed it all up. I've put the poison in there. I put the cat in there. I've sealed it all up and I shoved it to the side. And I'm waiting. Before I open it up, I don't know if the cat is alive or dead. But the cat can be thought of as both. Because when I observe, I force the cat into one state or the other. By observing, by opening the box, that is me forcing the cat to be either alive or dead. So there's this duality before opening the box that we don't know the answer, but it could be either. It could be both. We don't know. And what he was trying to simplify is this idea that electrons are like in a box. Before we experiment, before we observe, we don't know what that electron is doing. And there's an actual duality to its nature. Electrons have a duality just like the cat did. Their duality is called wave-particle duality. So the cat had the duality of being both alive or dead. And by opening the box, we forced it to be either alive or dead. It can't be both when we observe it. And the same thing goes for the electrons. The electrons have this wave-particle duality, this nature that is so difficult to understand. We try to observe it. But when we do, we force it to either act like waves or to act like a particle. And that's the problem with experimentation. We don't know how to observe both of these at the same time. And so with Schrodinger's cat, what we have to be able to think about is when we look at all of the experiments that are in this chapter 2 information, we will be looking at electrons in one of two ways, either as a wave or as a particle. But it's really the merging of those two ideas that gives us the holistic picture of how electrons behave. And so that's what I challenge you to do. When we think about the quantum realm, we gotta think that any time we are faced with an experiment, what are we actually looking at? The wave nature or the particle nature? So here's an example. Yes, they discovered that there is an absolutely small matter, extremely small pieces of matter, such as the electron, that behave much differently than a large macroscopic realm, right? The electron does not behave the same way as a desk does, but a desk is composed of millions and millions of electrons. So where's the difference? The absolutely small matter does behave differently because it's in a different world, right? They exist in two conditions. They either have wave nature or they have particle or matter nature. When we get into the macroscopic world, it's very difficult to see the wave nature. We see a lot of the particle or the matter nature. So an electron does have mass, right? And it does have volume. That's particulate, that's matter, right? And we can measure the mass. But under a different set of experimental conditions, it might have energy-like characteristics. This idea of bringing together wave-particle duality was a huge concept in the early 1900s. Back then, scientists did not know that matter could be the same thing as energy. They thought they were two separate things. Matter was matter, it had shape, it had mass, and energy, heat, or any other sort of energy was only contained in this other realm of energy. that had no mass whatsoever. But the electron is an interesting bridge between those two things. So what does it tell us about electrons specifically? It helps us explain that electrons exist and they behave in atoms in one of two ways. They can look like light energy, right? And they can express and they can absorb energy or release energy in the form of light. We will investigate that in spectroscopy next time. And we do know that they have mass and there is a position within the atomic structure, right? We talk about the electrons are just swarming around in that outer area. They take up most of the volume, right? And they're not a huge bit of the mass, but they're still physically there, right? So we're going to try to investigate both of these natures. The light nature is the one that is probably new to most people. Quantum mechanics is the foundation of chemistry. It explains our periodic table, which was developed before quantum mechanics. The periodic table was 150 years ago. Quantum mechanics was only 100. So the periodic table was set up, and now we can explain why it works the way it does. It's beautiful. We can also explain the behavior of elements in chemical bonding. That's something that we'll get into a little bit this semester, a lot in Chem 150, and even more in organic chemistry if you have the joy of continuing. And it also expresses the colors of their atoms. How cool is that? Fireworks. Why are some elements used in fireworks? It's because of the electrons and how they behave when we explode them. We'll talk about that when we get into spectroscopy. Super, super fun examples. It also predicts the atomic properties that are directly related to the behavior of the atoms. Why we have metals, why we have nonmetals, why when we exchange electrons in reactions, do some elements lose electrons and some elements gain electrons? Why are some elements just, practically inert, don't react, shoved up against the wall, don't participate in the party? And then some other periodic patterns. We will dive into a lot of these in chapter 3, next unit. All right, so just to wrap up our idea of a wave, this is what we're going to really dive into in chapter 2, the nature of light. We are going to focus our attention on the electromagnetic spectrum. Now, electromagnetic radiation is oscillating electric and magnetic fields. Electromagnetic radiation can be described as a wave comprised of these two different fields that are perpendicular to each other. So what we see is that that blue one is horizontal, flowing around there, and the red one is perpendicular to it on the vertical, up and down instead of left and right. And they both travel in a specific direction. Specifically for this diagram, that direction to the right. When we look at a wave, we can describe a few things. And those things that we can describe, first off, was amplitude and wavelength. Wavelength and amplitude are independent properties. Now, wavelength is from the distance from one peak to another. It's often abbreviated with the Greek symbol lambda. And it's often in units of meters or nanometers. Meters is the SI unit for length, but again, nanometers is a little bit more helpful for us in terms of our chemistry subatomic realm. Now, it's the actual distance between two peaks, or you can think about one oscillation, right? So what we see is this red one has a long wavelength. This one has a medium wavelength, and this one is a little bit smaller, this blue one, small wavelength. So we can call them long or large. We can call them small or short. all of those, because their distance descriptions are all very accurate. Now, amplitude or intensity is only the brightness. We will deal with wavelength more often because it's an intensive physical property, not dependent on the sample size. Amplitude is extensive, so it does depend on the actual sample size. Dim versus bright. And amplitude is going to be the distance from essentially point 0 to a peak. We'll call it midpoint to peak. We don't do a lot with amplitude. We'll see a little bit when we discuss the photoelectric effect, one of Einstein and Planck's #1 experiments during the quantum mechanical development. But again, we'll see that it's not super, super important. Now, wavelength is not the only way to be able to describe something of a wave. Frequency also is. Frequency is annotated as this script EV, nu, if you will, for the Greek symbol. It is the number of cycles or oscillations per given period of time. Most often, seconds. So if I want to just bring back another one of our waves here, let's just draw a wave. There we go. I can look at wavelength right here. There's lambda. It's not until I bring about, let's change it to green, the actual time that I can express a frequency. 1 wavelength, 2 wavelengths. So when we think about that per 1 second, that can be determined into a frequency. So frequency would be 2 per second, or seconds to the -1. You can write that a couple of different ways. 2 with a 1 over seconds. You can say 2 over seconds. Another unit is a hertz. 2 Hz. The hertz means literally per second, not the car rental place. Now, how we bring these guys together, these two extensive properties, is by looking at C, the speed of light. The speed of light is equal to 3.0 times 10 to the 8 meters per second. And what that is actually equal to is wavelength times frequency. Wavelength in meters, frequency in per second. So we can utilize this to convert, the speed of light is able to convert between wavelength and frequency, which are both very important values for us as we continue on in understanding the electromagnetic spectrum. We will practice with converting with these once we get into class. Here is our beautiful electromagnetic spectrum. Again, you do not need to memorize this, but this is just something to look at before we get into any calculations. What we generally see is that when we look at the wavelength versus the frequency here, long wavelength, or large number, corresponds to a low frequency. That's how we get the speed of light to be a constant. As one goes up, the other one goes down in terms of wavelength or frequency. Same thing over here, high frequency, short or small wavelength.